Hello. So today I will be going through a simple elliptic curve encryption scheme. And while I explain the mathematical steps, I'll also be working through an example. So my students who are watching this video, you can see exactly how I am creating a public key encryption system. So remember, these are the kinds of systems where any person who is given the instructions, which I'm going to be posting on the website, can encrypt a message, but only a person who has the decryption key will be able to uncover or decrypt what that original message was. So this is a method of allowing other people to send you secret messages. This is also our tutorial for the week. So over here I have my course website. If we just go to tutorial 10, I'm going to start a new discussion topic here. So this will be Octavia's public crypto system. So this talk will come in 3 parts, but I hope to have this in a single video. First part is, how do we build our crypto system? So this is what we do to allow people to send us messages. First off, we need to pick a prime that I'll call lowercase p, and we need to pick an elliptic curve, and we're using the same formula, y squared equals x cubed plus ax plus b. And all of these parameters that I pick on this slide are going to be public information. So I already picked these parameters before I started the recording. On the right side of the screen here, I have some scratch work that I'll be using through this video. So the prime number that Octavia is going to use is kind of a funny one. This is 23 ones in a row, and that is a prime number. And the curve I'm going to use, parameter A is going to be 97333, and parameter B is going to be this other number. So let me just copy paste that into my post. So that is step 1 complete. We've picked a prime, we've picked an elliptic curve. I've chosen this prime number to be large enough that we can send each other some kind of short messages, actually. We'll only have space for a couple, maybe like a word or two. If you want to encrypt longer and longer messages, you will need longer and longer primes. Okay, step 2. We're going to choose a point, capital P, that's on the curve, and a secret multiplier D between 1 and P. And then with both of these parameters, we're going to calculate another point, Q, which is D times P. So back on my scratch work, I've already selected the point P. The x-coordinate is 541, and the y-coordinate is 1729. So I'll copy paste those here. And I've not yet picked my secret multiplier. So let me go to random.org, because I'm not feeling terribly decisive today. So I want one random integer between 1 and, well, this doesn't go all the way up to the prime number I have. So let's take there's say 1 and 1 billion. I just need the one of them. So I hit my get numbers, and here is a random number 928945415. So that's going to be Octavia's secret number, and we need to write this down because this is going to be important for our decryption. So this part of the process does not go into the post. but I need to calculate what is d copies of the point P under the elliptic curve addition. And this is never something I'm actually going to do by hand. So I'm going to use this elliptic curve calculator that I've mentioned a couple times in the course. I have all my parameters already in here, and I want to calculate, well, this button is saying they want n copies of the point P. So for my number n, I will just copy paste my secret multiplier, and I hit calculate n times P, and here are my coordinates. So the x-coordinate starts 402, and the y-coordinate starts 564. These are some fairly large integers. So back to my slides. The points P and Q are going to be public information. People who are encrypting messages for Octavia need to know both of these coordinate pairs. But anyone who knows the actual multiplier, D, can decrypt the messages. So I've got to keep that secret. So here is my post, my prime, my curve, my point P, and I will now add the coordinates for my point Q right there. And this information is all that's required to encrypt messages for Octavia. So I'll just hit post to forum, and now anyone can access this information. Anyone who's a student of my class, of course, can access this information and send a message. So now we're ready for part 2. How do we encrypt a message? So as usual, the first step is we actually have to decide what message we want to send, and we need to turn that message into an integer modulo P. So this integer can only have 22 digits because my prime P has 23 digits. And just to make things easy on myself, I'm going to use this website letter numbers that I have linked in the slides. And I can type my message in. I'm going to use the setup where I have leading zeros on single-digit numbers and no dashes between them. Just make make things nice on myself. Goodness, I'm getting tongue-tied. So for a message, every one of my letters is going to end up being a 2-digit number. And if I have a total of 22 digits together, I guess that means I can have a message that's 11 letters long or shorter. So I'm just going to put in the name of one of my favorite albums. And here at the bottom, it just automatically tells me what that will turn into. So for later, let me just write down that my plain text was the phrase demon days and the number I get. I'll have to delete that space there. The number I get is 040513151404012519. Okay, so that's step 1 of the encryption process. Step 2, we're going to take this integer m and we're going to compute it according to the formula for the elliptic curve. So we'll take m cubed plus am plus b, and we want that to be a residue mod p. All right, so I have Wolfram here. My m is this, so I want m to the power 3 plus 97,333 times m plus my constant term. and this has to be a residue mod my prime. So I end up typing in this whole thing. So m cubed, a times m plus b mod p. I hit enter, and what do we get? Wolfram alpha says I get this number. 6 sextillion, and so on. So let me go to plain text. Let me copy this. This should be my x coordinate. So that's step 2. Step 3, we're going to check that our number actually has a square root modulo p. And again, there's another calculator we can do for this. And at this step in the encryption, because not every residue has a square root, we might actually fail step 3. So fingers crossed this will work. So here is another calculator. I've already put in my prime number p. I'll copy in the value of my residue. And if I press here, it will attempt to calculate the square root mod p. And we've got one. So good. We have succeeded in finding a square root. So we're on to step 4. So what's going on here is that if you do get this far, the lowercase m, which is our message, is going to be the x coordinate of a point on the elliptic curve. We just calculated that m cubed plus am plus b has a square root in this field. So that square root that I just calculated is going to become the y coordinate of my curve. So I'll copy that in here. These are my x and y coordinates for the point m, and m is the message. So if anyone sees this message, oh, excuse me, the x coordinate is my actual message, 04, 05, 13, 15, and so on. And this was the square root of the action under the elliptic curve. Okay. If your message gives you an x coordinate, right, and you calculate the square root and it tells you you didn't get one. Let's say, I'm going to change this slightly. If this ends in 2, 1, is there a square root? Show me something that does not have a square root. All right, so I'm having some difficulty just picking one out at random. If you're using this calculator and you end up with something that does not have a square root modulo your prime, then what you're going to have to do is you'll have to change your message. And probably the easiest way to do that would be to go back to your message and just add, say, a z at the end to change what your integer residue m is. And then that will change your x and y coordinates, and hopefully you will get a square root. So the short of it is, if you're not able to get a square root using this calculator, you're going to have to change what the message you're trying to encrypt is. So I was lucky enough that I didn't have to do that. Step 4 in the encryption is the step where I actually produce the ciphertext. So these are the scrambled messages that I can post online without giving away what the actual message is. So now, to encrypt, we need to pick another random integer. So again, from 1 to p minus 1. And we'll need to make sure that we have the coordinates for p and q copied down. So I still have these from my Scratch work. When you go on to encrypt a message, you'll need to have the p and q that belong to the person who you are trying to message. So the first ciphertext is going to be C1, and this is a point on the elliptic curve, which is k copies of the point P multiplied together. So k is the number that the person encrypting the message gets to pick. P is the point that the person who built the encryption system got to pick. So back on my Scratch work, I have the coordinates for P right here. I need to pick another random integer. So let me just hit again on random.org, and I have something new now. So I'll copy this down to my Scratch work. My secret multiplier for this encryption is 6283088847. So to calculate k times p, I'm going to go to the elliptic curve calculator. The prime p is already set. The a and the b are already good. The point p is good. So I need to take my multiplier, and I'll put it in the box for n, and I say calculate n times p. And that gives me some new coordinates. And I see that they are different coordinates from my q. That's good. That's what we want. So copy my x coordinate in, it starts 417. Copy my y coordinate in, it starts 398. That is the first ciphertext. The second ciphertext is the point C2, and this has the formula M, which is our message, plus k copies of Q. So the way that this calculator is set up, I can only do the multiplying and addition as separate steps. So my intermediary step is to take the coordinates for Q. This is what I got off of the post here, right? Coordinates for Q. Those will go in for what the calculator is calling P. And I need k copies of the point Q, so I'll put in the same k, calculate k times Q. And I get some new coordinates. I'm going to copy them into my Scratch work. So these are not yet the ciphertext. The ciphertext has the formula M plus KQ. So now I need to calculate the addition, the sum of 2 points. The first point is M, which is our message point. So let me copy those coordinates in here. The second point that we're adding is K times Q. Those are the coordinates that we just got. And I don't think we need to worry about the multiplier here. We're just adding 2 points. The calculator can do that work for us, and these are the coordinates we get. So coordinate 1 is 410 and stuff. Coordinate y is 335 and stuff. That looks good. So that is our ciphertext number 2. In order to send the message, we need to give both of these pieces of information. So on the post, let me hit reply. And I'll say a message for Octavia. And I'm going to copy in the values. Here is my C1, and here is my C2. So I can just hit submit, and now I've sent an encrypted message to Octavia now. The last part of the video, the last slide here, is how to decrypt a message. So now we're going to pretend that we are Octavia. We've been given the 2 different ciphertexts, C1 and C2. And the message is the x coordinate of the point M. I didn't post the coordinates for M, right? That has to be secret. So we can solve this using a little bit of algebra. Bear in mind that all of these formulas are happening inside the elliptic curve group, but the idea of solving an equation for M is exactly the same way that we would have done it from elementary, well, maybe not elementary school, but from earlier classes in algebra. So we know both the coordinates for C1, we know both the coordinates for C2, and because we're the person who built the encryption system, we know the secret multiplier D, right? You need to know what D is in order to write this formula down. So the formula for the decryption, step 1 says calculate C2, take away D copies of C1. And that's something that we can do using the elliptic curve calculator again. Algebraically, what's going on is that C2 is equal to M plus KQ. That's how we got those coordinates. C1 is equal to K copies of P, and if we're taking D copies of that, then altogether we've got DK copies of P. So D times K times P. On the second line here, I'm saying that Q is originally just D times P. That's how we got those coordinates when we set up the crypto system a couple minutes ago. So our formula simplifies to M plus K times D times P. So here's integer multiplication. Here is that many copies of the point P. And then we're subtracting D times K times P. So again, D times K is multiplication of integers. And we're taking that many copies of the point P with itself added in the elliptic curve group. So the integer K times D is really the same as the integer D times K. Order of multiplication does not matter in the integers. And if I have that many copies of P added together, and then I take away that same number of copies of P, they're going to cancel each other out because this is the inverse element to this one. So this formula will simplify down to just the point M, the message point. Let's go ahead and do that. All right, let's try this a second time. Had a small technical problem on the web page. So we're going to decrypt a message. Here I have the message that was sent to Octavia. I have two different ciphertexts, the C1 and C2, which I still have in my scratch work here. And what we need to do is we need to calculate C2 minus D times C1. So this gets a little bit tricky because the elliptic curve calculator does not have a minus sign on it. So as an intermediate step, I'm going to calculate D times C1. So my x coordinate, my y coordinate already in there. My D is this number 928 and stuff. Let's calculate D times C1. And I get coordinate 606. So that was a typo from my previous attempt. Y equals 796 and stuff. Okay. So according to the algebra, the message that I want is the difference between C2 and D times C1. This calculator does not have a minus sign on it. So what I'm going to do is I'm going to take the coordinates for C2 and I put them into P. There we go. And I'm going to take the coordinates for negative d times c1 and put them into Q here. What is negative d times c1? That's a good question. So these are the coordinates for d times c1. Negative d times c1 has the coordinates x equals 606 and stuff, and y is going to be minus the y coordinate from d times c1. So remember, in the elliptic curve addition, you negate a point by flipping the sign of its y coordinate. So let's see if the calculator can accept the negative coordinate here. See what we get. Calculate P plus Q. So we get x coordinate here, which was exactly our message, except we lost that leading 0. So it worked. Fancy that. That's step 1. Step 2 is to turn the x-coordinate of m back, take the x-coordinate of m, turn it back into text. So I'm going to take this x-coordinate, go to my letter numbers, and now I'm going to decrypt. So I will paste in that x-coordinate. And it looks a little funny here because I need to reinsert that leading 0. So when you go to do this, you might have to reinsert a leading 0 that got dropped off because the calculator doesn't like to have leading zeros on integers. Can't blame them there. But you can see I have now decrypted my message just from the numbers that were the numbers that I sent to myself, of course, and having the secret multiplier here handy. So that is the end of my example.